So as we get further into these problems, when you read a problem, it's not always going to say, okay, I mean, I don't mind that you do that, but if we're going to make lots of noises that are distracting, then we've got problems, okay? So as we look at this, and this isn't our living room, all right? If an object is moving at a specific rate, it's not always going to say the velocity is this. The acceleration is this, okay? The reason that's important is you need to look at the label. So how do you tell the difference between the two? Which is the velocity, which is the acceleration?
A or B.
That's the variable, but again, it's not going to say the velocity or V is this. The acceleration or A is this. So how do you tell the difference between if it's a velocity or an acceleration? And I understand that's when you're looking at your setup, it would be A and V would be the difference. But how can you tell the difference in a problem? Accelerations are meters per second squared, which means velocities must be measured in just meters per second. That's right. Okay? So of your velocity and your acceleration, which one can have a negative value, or is it both, or neither? Is there a negative acceleration? Which is a negative value? Yes. Yeah, you're on the right track. Accelerate or deceleration and have a negative value is the same thing. What about velocities then? That's correct when you say no. Okay? So all velocities are positive. Accelerations can be positive or negative. I always try to get a system and I set these in the same spot and I just have not. It always changes from day to day. Okay, so moving forward, it's a little bit of a preview on what next chapter is, and those are what we call forces. And we can make sense of this here in just a moment as you're writing this content down. Well, humidity's, I think, finally moved out of here, hasn't it? It's not so terrible outside. Really? I mean, you're expressing an opinion, and that's fine. It's cold in here? Oh, well, maybe. Well, let's see once what the thermostat says.
Turn it down. You like it.
Okay? And I don't know, I think it's comfortable. I think it's 72 degrees in here. That's just what the thermostat says. That doesn't mean that's what the actual temperature in here. Heat and temperature are related. They're not the same thing. Okay. And this, I believe, is the last thing that you have to write down. Oh, two of them. Okay. All right.
Unbalanced and interested in.
Right. Okay. Yeah, it's right here. because as we continue this speed video, okay, when it comes to race car driving, okay, inertia is always going to be an aspect of that and what can happen. And I'm not a racing fan. I do know some things about racing. Some people may choose, I want to go to a race because they like to see what, do you think?
Crashes.
They like to see the crashes. That it really doesn't interest me, but that's what variety is good. We're not everyone's the same. We all have different interests. Okay? Does everyone have this content that wants it? Then we got two more. Okay? Because we will be discussing, there's 3 laws. As you can see, here is the first one. Then gravitation, that's a shorthand way of saying the second law of what Newton had proposed. And then, as you would guess, there's a third one. And we'll get to that at a later time. Gesundheit.
What's German?
You got pen, ink all over them?
Yeah, it's like getting on the table with my paper and stuff.
Yes, you better go do that.
You know what the German thing is for bless you?
I just said it.
Gesundheit.
Right.
Yeah, Mason. It's German, not Spanish.
Okay. So finally, oh, that is it. Okay. Does everyone have this content that wants it?
Yes.
Okay. So one of the things that we've not gone over yet that I think is worth our time, okay, and that would be as follows. I butchered that. I didn't write it very clearly. That's what that means. Okay. That's probably a little too fast. Okay, so once you get that wrote down, then I want you to find your formula sheet. That is correct. So I'll give you a little bit of time here rather than having awkward silence. So what we see here is we have a variable can stand for anything. And what that means is when you are solving for unknowns in your algebra class, maybe you have a whole bunch of problem sets that might look like, maybe you have 3x minus 2 equals 10. Okay? Maybe it doesn't have 3x minus 2 equals 10. You could have 3b minus 2 equals 10. You could have 3y. Why? Because. Yeah. Yeah, why? Because. All right. So just out of curiosity, I think the answer is 4, isn't it? Is that right? Right? Okay. So what we mean by that, when you have these formulas, you can use any variable. But to us, in the author, it just makes sense to use the one that's the most practical. Because you could do this, you could say momentum, M for momentum, because usually you use the first letter of whatever it is you're solving for. Velocity is V, acceleration is A, right? Okay. Can anyone see why you might not want to use M for your variable for momentum?
Because the word is momentum. Could be mass.
Because you could use that for a mass as well, and you wouldn't know the difference. So in this case, when we're talking about P for momentum, it's just a product. It's a product of an object's mass times its final velocity. Notice we don't have initial velocity here. And the reason for that is if you don't have a final velocity, it's just an initial one, that's where an object starts. And 1, it might not be moving. 2, might not be moving very fast, but we just attribute this to the final velocity in this equation. Again, you can use whichever variable that you want, just as long as you know what it stands for. Because a little later this semester, some of these do repeat themselves throughout the semester. Don't write this down yet because we haven't covered this yet. Because this is referring to power equals force times distance divided by time. Okay? So what you would do, and what we'll illustrate in this class, maybe you put a line over it like that. But again, you can use any variable that you want for these. Okay. So in this case, you've read the problem. What is the next thing that you should do? Just like we've been doing for a little over a week now. Just barely. What do we do next? Okay, which means what? Okay, so we have a velocity. What else do we know? Okay, in this case, all right, in this case, a mass, it can be kilograms, it can be grams, it can be tons, it can be any sort of mass. It doesn't always have to be kilograms. Okay? And then finally, we don't know what the momentum is. Okay? So, once you have this wrote down, then you just look at your formula and do what the formula tells you to do, which means we've got an equal sign. What is on the left-hand side of that equal sign with the formula you just wrote down? Okay? And what did we say back there? So what? Air? Where do you get air from?
There was nothing on your side.
I guess I don't know. I tell dumb jokes too, but that was the why and because. Okay. So what's on the right-hand side? Okay. Okay. And what else?
145.
Now, I don't know. I just put these in parentheses. You can put an X between there, whatever it is, or a dot, not a decimal, whatever it is that you feel more comfortable with as far as illustrating a multiplication. Okay? So, what does the formula tell you to do? Yeah. And what do we get when we multiply those? 1,400. Okay? Okay, one person, not five. One person only. What is it?
0615.
0.15? Okay. So then our label is what we call derived. That's not right?
No, there's no 1 in front of the 5.
Okay.
It's just 5.
So I'm choosing to put that 0 there. All right. So then this is what we call derived unit, which means we've got a mass here, okay, and here's our velocity. And when we label these, since we're multiplying them, this is what we call a kilogram per meter over seconds. You're not subtracting that, okay? You are illustrating that is that for every kilogram of that object, it's moving at a specific speed. So again, it's not kilograms minus meters over seconds. It's kilogram per meter per second.
So is that the label?
That is the label, yes. Because maybe it's something that is much larger.
Why did you flip them?
Why did I do what?
Isn't it supposed to be 9.7 meters per second? And then 145 is the kilograms.
Oh,
Yeah.
oh. Okay,
Sorry. I was worried there.
all right. I did that on purpose.
Yeah.
All right. So then, this could also be, maybe it's a very large object to where this could be 1.45 tons. Okay? Then this is tons over here, which then means you would put that down here. Ton per meter per second. Not minus, okay? Because if you keep saying it that way, you're just going to confuse yourself, okay? It's a per meter over second. All right. Front right, we on the bus? Okay. Back right, middle. Okay. Front left, back left. Back left. Okay. Front left, okay? Front right, middle. Middle, middle, right. Middle, middle, left. Okay. Back left, middle. Okay. And right, no, left, middle, middle. Okay. And back right corner. Okay. I think that's everybody. Okay. So I want to go ahead and continue this for just a few minutes.
Oh, my pencil.
Yes. Because this illustrates inertia, and I want you to see that concept.
Is this video actually real?
Wait, what's inertia?
Hey,
Yes.
I got those too.
Inertia is a resistance to change in motion. We just talked about that. Okay? Do you believe me back there?
Believe you about what?
It says it right here. Inertia. Okay?
Inertia.
Inertia, I barely met. Oh,
Oh, I didn't want that.
Show them you won't.
Okay. We won't watch a whole lot of this.
Speed is what makes auto racing. Split-second maneuvers, close formations, all at high velocity. In this world that lives for speed, drivers must constantly push their cars harder and faster.
The driver's always trying to find the limit on the car. You know, how fast can I take this corner? Can I go a little bit faster?
Okay. This is what I want you to watch. This is a critical part of this. Yes.
Can I go to the bathroom?
no.
Really?
Yes.
Just doing it so you can get another video. No. I just heard you telling Levi that.
But high speeds can take a deadly turn.
Sometimes you just take it a little bit too fast, and the car just doesn't have the grip, can't take that speed, and you lose control of the car and hit the wall.
So what that's saying is, what would you guess that we just talked about is pushing that vehicle up against the wall? Starts with an I. Inertia. Okay? And for those of you who, it's been a long time, but Disney's Pixar Cars, you seen that movie before?
Yeah.
One of the things they talk about, okay, when you're going around curves, if you want to go left, you have to turn your vehicle to the right. Okay, so what is it? Speed McQueen or something? Lightning McQueen. Okay, wants to go around a corner, but he doesn't know how to do that, and he has that problem because he keeps telling himself, "I got to go to the left." So he turns his wheels to the left. The car spins out every time. Inertia is causing that, and that's what we see here.
On average today, there's one serious injury for every 300 speed racing accidents. 40 years ago, that ratio was 1 in 10.
When I started IndyCar racing in the late 60s, we lost a guy a weekend. Basically, it was a tube frame car with a 70-gallon fuel tank on the back, and the driver just hung out in the open. There's nothing to protect him.
High-speed crashes have been part of auto racing since its earliest days. In 1911, the very first Indy 500 had a multi-car pileup just 13 laps into the race. As cars got faster, auto racing dangers increased. The 1958 Indy race saw one of the industry's deadliest high-speed crashes yet.
Car number 5, the Zinc Special, is the first to wreck, another over the wall, and we've got 1, 2, 3, 4, 5, 6 cars piled up here on the northeast turn.
The fatal flip of driver Pat O'Connor's car that day led to mandated metal roll bars and medically certified helmets to protect Indy drivers from some of the hazards of speed. More recently, in the 1980s, carbon fiber replaced steel plates and aluminum tubing in race car construction. That's made race cars lighter, yet stronger. In a high-speed crash, Today's race cars will absorb most of the impact, deflecting it away from the driver.
So when you crash, everything disintegrates. All these suspension parts, the wheels, the front wing, everything is designed to break off the car fairly easily, and that way the impact it's absorbed by the car, not absorbed by the driver.
Here's how it works. A car in motion builds up kinetic energy. The heavier the car and the faster it goes, the more the kinetic energy is built up. A 3,600-pound racing car traveling at 180 miles per hour has enough kinetic energy to launch an average man 5 miles into the air. If that heavier race car runs head-on into a concrete barrier, the kinetic energy is released all at once, with the force being absorbed by both car and driver. But a crash with a lighter car that can spin, tumble, and shatter releases the kinetic energy over a greater period of time, dispersing the force. As race cars continue to go faster, newer safety features are constantly being tested, like these speed-absorbing barriers. They're called safer barriers, or steel and foam energy reduction barriers. As this test footage shows, the vehicle slams into the barrier with tremendous force, but the wall compresses, absorbing the energy of the collision. The outer layer closest to the track is made of hollow 8-inch steel tubes, which are both strong and flexible during a high-velocity impact. The center layer is dense 22-inch thick polystyrene foam, which absorbs energy by compressing. The inner layer nearest the spectators is solid concrete to provide resistance.
With soft walls, there's a certain amount of elasticity, and the driver has a fairly good chance of being able to survive a fairly strong impact against those walls.
With auto racing on the fast track, safety elements like this are the first line of defense against the dangers of speed. Road speed has raced us along our top 10 countdown, with a supercharged Boss Hoss at number 6, and the high-impact World of Car Racing at number 5. We're 2 steps closer to crossing our countdown finish line with number 1, that can travel at never-before-seen speeds of 7,000 miles an hour. We're blasting down this countdown to our fastest marvel at number 1. We sprung out of the gate at number 10 with the remarkable expeditionary fighting vehicle, and have raced our way down to the blistering speeds of auto racing at number 5. Now, at number 4, we're pushing the accelerator as hard as we can, but this time on water. It's the world's fastest watercrafts, hydroplanes. If you thought flying 200 miles per hour around a track was a thrilling challenge, try racing a craft at that speed on water.
These are a 3,000 horsepower bucking Bronco. Everything about it's difficult to control, and a lot of times you're not in control. We just try to do the best we can.
Dave Villwatt holds one of the world's hydroplane records at 220 miles per hour. As a hydroplane flies across the water at full throttle, only its propeller is below the surface.
A hydroplane is part airplane, part boat. On my right foot, we have a throttle pedal that controls the engine throttle. On the left side, we have a flight control pedal, which controls a forward flap that either makes the boat go up or down. So we're flying the boats like you would an airplane.
Reason enough to put these supercharged watercrafts at number 4 on our countdown. Where does a hydroplane get extreme speed? Where else? Extreme engine power. At the Turbine Engine Warehouse near Seattle, Washington, they're testing this 3,000 horsepower hydroplane engine.
The turbine engine makes horsepower in 4 stages: intake, compression, combustion, and exhaust. And that makes a very efficient engine.
In stage 1, the turbine engine takes in air at 300 cubic feet per second. Stage 2, The air goes through a compressor, which pressurizes it to 90 pounds per square inch. Stage 3. The air is combined with fuel in the burner can and is ignited. And finally, stage 4. The supercharged hot gases spin the main turbine assembly. Think a speed-making engine like this requires exotic fuel? Think again.
What we have is basically home heating oil, which is essentially kerosene. We use kerosene because it's a very stable fuel. The risk of fire in the boat is very low. And also we can extract a lot of energy out of every gallon of fuel versus a lot of other fuel.
But racing at speeds over 200 miles an hour on the ever-changing surface of water means drivers are put to the ultimate test.
You're essentially an accident waiting to happen. When you're going so fast, you cover a football field in a second. So when you're looking for something to happen, you're looking way down the track.
Ken Muscatel is a hydroplane driver who lost his battle with speed in a spectacular crash in 2004.
The boat was going good, about 185, not super fast, and all of a sudden it just starts lifting. And it's not coming down, and it goes higher and higher and higher, probably ended up 60 feet in the air, flew all the way around 360, landed on its tail, slapped down back on the water, broke the boat in half, but was kept going, so I had to shut it off, and I just waited for people to come. I felt lucky to be alive. Lucky not to be hurt, and still disappointed because we weren't going to be able to race the boat.
But dangerous speeds and all, hydroplanes continue to push the velocity envelope.
Bottom line is, in the future of hydroplane racing, I see more technology, more power, faster race boats.
With the aquatic thrills of the hydroplane charging out at number 4, we're just 2 speed demons away from revealing the fastest of all. But before we get there, strap yourself down for number 3 on our speed countdown. There's some of the fastest road vehicles on Earth. Top Fuel dragsters. If there's one place that showcases top speeds like no other, it's a drag strip.
Speed's very addictive. It can make you do things that some normal people wouldn't want to do.
These are the fastest accelerating vehicles on Earth. Top Fuel dragsters and their counterparts, known as funny cars, can rocket to speeds of more than 300 miles per hour while scorching a 1,000-foot track in under 5 seconds. They're power-driven by supercharged engines of up to 8,000 horsepower.
Everything out here is about horsepower. Speed, elapsed time, it all comes down to horsepower. When you're talking 330 miles an hour, 8,000 horsepower, I mean, it's such an animal, these cars.
Melanie Troxel has been one of drag racing's top drivers.
The car doesn't know whether there's a male or female in the seat. It's, equal all the way around for all the drivers.
Like all drag racers, Melanie Troxel gets to experience our number 3's blistering speed thanks to supercharged engines. Astonishingly, once stripped of their massive air intake funnels and exhaust pipes, at their core, these engines aren't much different than those of the high-performance 8-cylinder sports cars on the road today. The difference is what goes into the engine.
The secret to making between 7,000 and 8,000 horsepower on one of these 8-cylinder engines is the fuel. We pour nitromethane into the fuel tank. We distribute it with a massive fuel pump into the engine. We put the air into the engine through an injector which has got a supercharger under it. It sucks all the air into the engine. We mix those two in each cylinder. We light it with a big magneto, and that's what makes all the power.
Nitromethane is like gasoline on steroids. In a 1,000-foot 4-second run, a dragster will burn up to 15 gallons of nitro. That's an 80th of a mile per gallon.
Nitromethane over the years has proven to be a very powerful fuel. We've learned to tame it and put it into these engines to make the maximum amount of horsepower with the air ratio that we have.
It may be speed boosting, but nitromethane is also extremely volatile, as Melanie Troxell discovered when her engine exploded during a race. Luckily, she escaped without injury, and even won the race. But close calls like this are a regular part of the high-speed lifestyle for racing pros like Melanie Troxell and Tommy Johnson Jr. These speed addicts face risks on the track every day.
Safety concerns, we both know what can happen, the ultimate price you might pay, and we both accept that, and you understand that.
Because they've never raced each other, the question still remains: who's the fastest?
Well, you know, they say women have better reaction times, actually, in these cars. So if that's any indication, I'm pretty sure that I'd beat him hands down on the track.
I'm going to beat her just like anybody else out here.
With the aquatic thrills of the hydroplane at number 4, and the supercharged velocity of the Top Fuel dragsters at number 3, we're rocketing down to number 1 in our countdown. Any guess as to what it could be? And how fast it can go? There are many high-speed marvels to choose from, but only one is the speediest of all.
Okay. Go ahead and stop there for today. I will hand out your paper. Don't forget you have yesterday's paper due tomorrow, and you have some vocab terms due tomorrow as well, and you have an evaluation, the first big one, on Thursday. We'll catch up to you next time.